Hello, everyone, and welcome to our live session. My name is Matthew, and we are happy to have you here on our February 28th live session for our online classes. And for those of you who are finding us through YouTube or through some other venue, we are happy to have you here as well. I am one of the online staff and instructors for our online classes. We are going to answer a bunch of questions from everybody in the chat, so please post your questions in the chat. We will get those from there, and we tend to jump around a bit. Make sure you subscribe to our channel so that you can find out about upcoming live sessions. And please ask your questions only once. We see all the questions in the chat. We try to keep things at an introductory beginner level here. And so if I skip your question, it's because either you've asked one or we've covered that topic. But we will get around to those topics. Chris, why don't you welcome everyone, and then we will get started with the questions from the chat.
Okay, welcome everyone to the live session associated with our online classes, or however else you found us. And we'll just get started right away with any question on astronomy.
Excellent. The first question is from Life, and the question is just really what's the origin of reality, and what will the end of reality look like?
Well, philosophers have argued about reality for 2,500 years, since the ancient Greeks first asked these kind of questions, and it's obviously not an easy answer to give what reality means. We perceive reality through our senses, and we process the sensory information in our brains, and so we construct a model, a mental model, if you like, of what's out there in the real universe. The idea of reality is slippery just because our brains are not 100% fidelity on what the world outside contains. None of our senses are either. So we can misperceive things, we can see things that are not there, we can not see things that are there, and so on. So that's why philosophers argue about this. Reality is an important concept in philosophy. Astronomers and physicists don't worry about it too much. They just worry about what the laws of nature and the laws of physics are, and how they apply through the universe, and how we can learn about those through observations. And even then, we don't imagine we have a full sense of reality, but we are just working our way towards a deeper view of the way the physical universe is.
Excellent, thank you. The next question is from Adrian Murray. There seems to be no end to the plethora of subatomic particles. The standard model is based on scientific theory. Could the rest of the particles we do not understand be not rationally organized?
Well, the standard model of particle physics has a core set of particles that hasn't changed really for quite a while. It consists of three families or generations of quarks. These are the fractionally charged subatomic particles that form atomic nucleus, protons and neutrons, as well as mesons, or intermediate mass particles. And then it consists of a sort of parallel track of three families of neutrinos, the electron, mu, and tau neutrinos. And then there's a whole set of evanescent particles. So the zoo of particles that the question is referring to are outside that core set of stable particles. There are many, many particles, hundreds, that can be produced momentarily in high-energy collisions at accelerators, and they have very short lifetimes, so they don't exist stably in the universe. So they're not necessarily part of our construct of high-energy physics, because we understand how with energy we can create transient situations. For instance, there's exotic particles called pentaquarks that are 5 quarks that briefly join together, but they don't exist in nature. Protons and neutrons are each made of 3 quarks, and we don't find stable pentaquark particles. So there is a large number of subatomic particles, but the core set is actually quite small.
Excellent. Lots of atomic physics questions or quantum mechanics questions today. Mustafa, who's on with us live, asks, why do we need to study tiny quantum particles in order to understand the working of the universe?
So the issues of microscopic physics are important for the universe as a whole because the mechanisms of the universe involve atoms and how they behave. These connections are very direct when it comes to the Big Bang because the universe in the Big Bang theory was once as small or smaller than an atom. So we actually have to consider subatomic processes when we consider the instant of the Big Bang, the origin of the universe. But even in the older, colder, larger universe that we occupy now, quantum principles are important. This is how we learn what the universe is made of, the principles of spectroscopy, of how atoms and molecules change their quantum energy states and allow us to identify elements by their spectral fingerprints. The fusion that takes place in stars is based on quantum physics, and so that's how we understand how stars shine. And I could give many more examples, but basically atomic and quantum physics permeates astrophysics on all different scales in the universe.
Excellent, thank you very much. The next question is from one of our live viewers, Nagar, who asks, hi, when two particles become entangled, how do they stay connected? And does this connection depend on the distance between them?
So the act of creating entanglement in a laboratory situation does involve special conditions. Often it involves very low temperature. It involves isolating the particles concerned and bringing them into proximity where their quantum states can become coherent. The issue of how far they can be separated while maintaining that coherence of an entangled state is an interesting situation that is explored in lab physics. And so far, entanglement has been easily demonstrated over meter-length scales in the lab and very indirectly over much longer distances, even between continents. So entanglement has to be created with special physical conditions. Normal atoms in a normal object are not entangled in this way. So it implies a coherence of the behavior of the quantum particles, which really does require their isolation from other confusing effects.
Thank you. The next question is from one of our participants who sent an email. Dave McKenzie asks, good morning. Are there any laws going to be put into place to help control space junk around the moon and Mars as we step further out into the solar system? It seems to have become a serious problem around Earth.
It's true. Space junk or debris in space is a serious problem. The number of satellites is booming at the moment due to constellations launched by Starlink and SpaceX and other companies. So the number of Earth orbiting satellites is going to grow from roughly 20,000 up to 100,000 by the end of the decade. And it's really the smaller pieces of debris from defunct satellites or things that collided with each other in space that are causing the problem. The moon and Mars don't have a particular space junk problem because we just don't have a lot of activity there. Earth orbit is where the problem is. Is anything being done about it? Well, unfortunately, nothing very effective at the moment. At least all the people involved, major space companies and private space companies and government space agencies, are paying attention to the problem. They understand it's unsustainable and it's a damage to the whole activity of enterprise in space. However, beyond that, it's not clear what will happen. There's a working group of the United Nations that's trying to work towards a sort of treaty language that would get countries to sign on to mitigate space junk, that is to clean up after themselves when they launch big satellites by deorbiting them, or even employing technologies to sweep away debris that exists, but that's a very hard job. The UN works on very long, slow timescales, and so that working group has existed for years and hasn't produced anything yet.
The next question is from Norman, who's on with us live. Recently, the brightest object in the universe was discovered, the quasar with a black hole whose mass is 17 billion times the mass of the sun with an accretion disk of 7 light years. It's certainly a massive beast. What does that do to the resident galaxy?
So a black hole that large clearly has an effect on the surrounding galaxy, especially when it's active and emitting radiation. Typically what happens when a quasar is in an on state, because quasars also have quiet states where the black hole is not accreting and the object is just a large gravitational mass that is not having much impact on anything else except by the gravity itself. When the quasar is on, however, in this case, it would evacuate the central regions of a galaxy, hundreds of parsecs of gas and dust, and then essentially quench itself. So there's a sort of cyclic process that happens where quasars get active as they accrete mass, especially when they're that big, and then they eject winds and high energy particles that blow away the gas that they would feed on, and so they have a quiet patch or a starvation phase. And this quasar probably is operating similarly. That's about the maximum ever observed for a black hole. I've read of a few examples around 20 billion solar masses, but 17 billion we think is pretty much the practical limit for black holes in the universe.
The next question is from Rut Arut, asks, in Are We Alone, you likely touched upon the concept of extremophiles on Earth. How do these organisms inform our search for life beyond our planet?
So extremophiles are mostly microbial creatures on the Earth that have occupied niches in the environment that have conditions that we could not tolerate, that humans or most plants or animals could not tolerate. And that includes a very high temperatures above boiling point of water or below the freezing point, very high levels of acidity or very base contents, toxic metals, extreme dryness, very low amount of water, even though life does need water, and so on. There are all these possibilities. And life exists in these situations. What is telling us about life beyond Earth is that in living environments beyond Earth, we have to accept the possibility that life will adapt to places that we consider uninhabitable. So when we talk about a habitable zone, as astronomers do, that's a very restrictive definition of a balmy region somewhere between the temperature of frozen ice and boiling water, and that life can survive. But life can go outside of those bounds. So it's telling us that life outside the Earth is more robust and likely is going to inhabit some regions that we would consider uninhabitable.
The next question is from one of our live participants, Andrew. Why are people afraid of the star Betelgeuse, which is 700 light years away, when there's Sirius basically next to us at like 8 light years away?
Well, Betelgeuse is the red supergiant, and it is in the late stage of its life. And when it dies, it will be a cataclysmic supernova explosion. And so there's some concern that even at that great distance, if it's the most dramatic type of stellar detonation, and the energy is maybe preferentially directed towards us, that could be hazard to the Earth. Sirius is not going to die that way, and is probably not as near the end of its life as Betelgeuse. So that's why Betelgeuse gets a lot of attention.
The next question is from, it's kind of a generic username. What is it like in 4D space, and why can't we get to know it other than through mathematical understanding?
Well, we do inhabit four-dimensional space, by which I'm taking it to mean the space-time of Albert Einstein and general relativity. That's 3 dimensions of space and 1 of time, and they're coupled, tightly coupled through the equation, so we have to think of it as one thing. Our experience of four-dimensional space-time is a little decoupled, because we experience space, the 3-dimensional region we occupy, and then separately and psychologically and biologically we experience time as something that moves and flows in one direction and never in the other direction. So these are, to our experience as humans, these are quite different categories, the space and the time. So we do not experience space-time in the mathematical sense of space-time. And I think that's why it's hard for us to envisage what it really is like mathematically. But our experience, as much as it's different for the sensing of time and the sensing of space, is governed by general relativity.
The next question is from Irina, who asks, if we prove string theory, does that mean that there are parallel universes?
Not necessarily. String theory is still a frontier physics theory that seeks to explain fundamental particles and some of the problems associated with standard model of particle physics, in terms of particles not being small round objects but actually being tiny one-dimensional strings, where the one-dimensional scale is 20 or 30 orders of magnitude smaller than a typical atomic scale. This solves certain problems in quantum theory, and it sort of unifies the fundamental particle zoo in terms of a single unitary phenomena of strings. Strings themselves don't imply parallel universes. If the string theory is correct, then that's a deeper level of reality for nature than the particle description we typically use. But the parallel universe concept emerges more out of cosmology and the Big Bang than it does out of string theory.
Wendy Traver asks a question through email. Is infinity just a mathematical concept, since even the universe seems like it must be finite?
Infinity is definitely a mathematical concept, and it's a very rich mathematical concept. Books have been written about infinity, and there's more than one infinity in mathematics. In physics and in the universe, infinity is more of a concept. It's not necessarily it's strictly mathematical form, because it doesn't really make sense to have an infinite universe. For example, in a universe with, as Isaac Newton knew very well, an infinite universe filled with objects would have infinite gravity, and that's a problem. You can't calculate the infinite gravity of a universe. Universe infinite in extent, filled with stars and galaxies, would have an infinite amount of radiation and light, and that's also not easy to understand in physics terms. So when numbers blow up, and they're physics numbers like light or mass or energy, then infinity is not really meaningful, because we don't imagine that can be the case in the physical universe. So I think there's a fairly strong distinction between mathematical use of infinity and the physics use of infinity, especially in cosmology.
Jim is on with us live and asks, could black holes be converting matter into dark energy?
We don't know, because what goes on inside the event horizon of black holes is sealed off from us. It's information we can't have. And so it's just speculation. But there's no particular physical reason to connect what happens inside a black hole with the phenomenon of dark energy. Dark energy is not a sort of localized thing that could occupy a dense region like the interior of a black hole. It's a global phenomenon that applies to space-time itself, the fabric of space-time, and causes it to accelerate in its expansion. So there's no very good link between dark energy and black holes, which means any speculation about whether dark energy can be created in black holes is definitely just speculation.
The next question is from an email from Ravi, who asks, I understand that shock waves from supernova can induce star formation in molecular clouds. Can gravitational waves from supernova or more cataclysmic events like mergers also cause stars to form?
Not really. Gravitational waves are space-time ripples or perturbations that travel through the universe at the speed of light. And that flexing of space-time as caused by a supernova is detectable, of course, as we found with the LIGO experiment starting in 2016. But it's an extremely subtle effect. It's shifting space-time by distances or scales that are smaller than the size of a proton. So there's not simply enough motive force in a gravitational wave to compress a gas cloud and cause star formation. The shock waves that a supernova emits are shock waves in the gas, in the plasma itself, and that shocking of the plasma will compress it and will very rapidly trigger star formation. So that's a very effective mechanism, and we think we understand it.
The next question is from Sphere, who's on with us live. Hello, Professor. My question is, do you think that we are in a crisis in cosmology right now? I assume they mean that there are some, thing that the field is stuck on or, can't continue with.
So the two regimes where people talk about a crisis in cosmology are the one that's bubbling up in the last few years is what's called the Hubble tension, the fact that the measurement of the local expansion rate of the universe from indicators like Cepheid variables and so on is discordant, and supernovae is discordant with the high redshift or early universe measure of expansion from the microwave background. So if you're telling a consistent story of the expanding universe, you have to be able to connect the locally measured expansion rate with the expansion rate inferred at an earlier epoch. And the disagreement of those two, which has now been shown to be significant at 5 or 6 sigma level, so it's statistically highly significant, is not easy to explain. That's one crisis. The second broader crisis is the fact that after 60 or so years, we still don't know what dark energy is, and after almost 30 years, we don't know what 60 years, we don't know what dark matter is, and after 30 years, we don't know what dark energy is. And these are the two major ingredients of the universe. So while we are in a state of ignorance about the two main ingredients of the universe, people speculate that maybe some core aspects of modern cosmology are not correct, and that's a crisis of sorts. Not everyone signs on to that second crisis, although the first crisis, the Hubble tension, does not seem to be going away.
Excellent, thank you. Excuse me. The next question is from an email from Hernan Reyes, who asks, regarding some interesting articles on the New Horizons spacecraft and discoveries, can you talk a little bit about the so-called scattered disk and what it is that contains the Kuiper belt objects or Kuiper belt objects, how and why it was formed, and why do these KBOs have elliptical orbits that are steeply inclined to the plane of the solar system?
So the outer solar system is getting more information with New Horizons, as we've finally got some probes going into the outer solar system. These are very hard objects to observe from Earth because they're 40, 50, 60 billion miles away and they're small. So the rocky material in the outer solar system is hard to study from Earth-based telescopes. But we do know of the Kuiper belt, and the Kuiper belt is a region of rocky material at sort of subplanet size, or smaller than Pluto down to asteroid size, that extends from about 40 astronomical units to 80. And recent work on the New Horizons probe have indicated that the belt extends further than we thought. We thought it pretty much tailed off by 60 or 70 astronomical units, but we actually see it goes substantially further, maybe all the way out to 100 astronomical units. The highly inclined orbits of some of that material are most readily explained in terms of Neptune. So the largest, the ice giant planet Neptune, the outermost planet, given that Pluto has been demoted to a dwarf planet, has substantial mass, and its interactions with material in similar orbits will kick it into, often depending on the angle of incidence of the interaction, can easily kick it into a highly inclined orbit. So we know pretty well of a mechanism where Neptune will scatter material in the Kuiper belt both out to larger radii and also into inclined orbits.
I will go ahead and ask the follow-up question since it's highly related. It seems that New Horizons has detected more interplanetary dust than expected to be found in the outskirts of the Kuiper belt. How has this excess dust come to be, and what's the significance of the Kuiper belt ballooning to a much bigger size than previously thought?
So the issue of interplanetary dust in the outer regions of the solar system is an interesting one because we just haven't had much data on this until recently. New Horizons telescope is not able to fully characterize the dust, so these are quite subtle indications of dust. And it's not an entirely unprecedented result. What we found as we realized the Kuiper belt is more heavily populated and more extensive than we thought, we've also been able to update our calculations on collisions, naturally occurring collisions in the Kuiper belt. And these collisions will gradually grind down the rocks towards dust particle size. This is a process that happens in the inner solar system too. It happens in the asteroid belt, it happens in the ring systems of the giant planets. And so we have a sort of grinding mechanism that will degrade material to dust-sized particles. And it looks like that process has been operating in the Kuiper belt, leading to a fairly significant amount of dust between the larger rocks.
The next question is from Faisal, who asks, does deuterium-rich water support life?
Yes, deuterium-rich water can support life. Deuterium is an isotope of hydrogen, and it has an extra neutron. And so deuterated water has a different molecular weight than normal water. But functionally, it's very similar. Deuterated water has many of the same properties as normal water. It's a highly polar molecule. It exerts surface tension. It expands when it freezes, and so on. The major characteristics of water that facilitate or are invoked in the biology of the Earth would apply in deuterated water as well.
The next question, is a kind of a follow-up. So is the water that we have explored or found on the moon and water like the water that's on Earth, or might it be higher in deuterium, or just could it be another form of water?
The water that we found in frozen form on the moon in sheltered craters like the Shackleton crater on the moon's south pole and elsewhere in shadowed regions of craters is almost certainly normal water. It's just H2O, familiar from the Earth. Some amount of it, some small fraction will be deuterated, as is true on the Earth. And this happens when water interacts with high energy particles. It can actually change the chemical structure and cause the isotope of hydrogen to be engaged with oxygen and then form the deuterium water molecule. But it's a very small component of the water on the Earth, and we don't really measure it very well on the moon, so mostly we think it's just normal water.
VF Kumar, who's on with us live, asks, can we make a time machine?
Not so far. So time as a arrow that flows forward and never goes backward is a principle of physics, essentially. It emerges out of thermodynamics and the laws of thermodynamics. And so we see reversibility at the subatomic level in terms of fundamental particle interactions, but from macroscopic objects, big objects like humans, you cannot make time go backward, and therefore there is no way to make a machine that would make time go backward. As far as we know, that would violate physics as we understand it.
The next question is from Root Meloria, who asks, what extreme environments on Earth might serve as analogues for extraterrestrial habitats?
People study extreme environments on the Earth that are analogues of some extraterrestrial habitats. The two environments that are used as Mars analogues are typically the Atacama Desert in Chile, the high Atacama Desert, which is extremely dry and high altitude, so the air is thin. It's not quite Mars-like, and also can be cold too. And then volcanic craters like Mauna Kea and Mauna Loa are used for training for Mars missions. So we have some very arid Mars analog environments. For other environments beyond Earth, we might imagine a deep sea environment. Life possibly started near hydrothermal vents and far from Darwin's warm little pond on a shallow sea. So we think those environments probably exist elsewhere, since we know there are many water worlds among the exoplanet inventory. And so some of those with volcanic activity, because they're massive enough to have tectonics, would have subsea volcanoes that could facilitate life, just as it may have started on the Earth. So there are a number of ways that we can imagine extreme environments beyond the Earth, but we can't characterize exoplanets in enough detail to really see these environments up close.
The next question is from Astro Taha, who asks, we know that time tends to slow down near the event horizon of a black hole. So is it possible for the person who's falling in the black hole to see the black hole evaporate and disappear beneath them?
Well, no. The irony of relativity is that while, as viewed from the outside, the time or a clock falling into the event horizon will gradually slow down and will asymptotically, time will freeze, essentially come to a standstill at the event horizon. The experience of someone or something falling in is that their time runs normally and they fall into the black hole. So someone falling into a black hole would not get to witness the black hole taking its very slow time to evaporate in the future, because they'd fall into the black hole quite quickly on a ballistic time scale just by gravitational infall close to the speed of light, and then time would flow and eventually the black hole would evaporate.
Next question is from Suhail, who's on with us live. I have heard that the laws of physics work only after the Planck's time duration. So what was it like between the Big Bang and the time before the laws of physics worked?
It's a good question, and the simple answer is we don't know. We work backwards from the present universe towards the Big Bang, knowing that the universe started in a hot, dense state. And the point at which our physics fails us is the Planck scale. So there are physical numbers that you can calculate that invoke Planck's constant because they're about the smallest subatomic scale, and that's the Planck scale, a length, the Planck time, which is 10 to the minus 43 seconds, the Planck energy, and so you can have, and a Planck mass even. So you can have fundamental quantities in terms of Planck constant that define the limit of our knowledge because we don't have a quantum theory of gravity. So there's no gap there. There's just incomplete physical theory basically that stops us from doing any calculations.
The next question is from Mark, who asks, what is your estimate of what percent of atoms in the universe today were existing at the Big Bang?
Well, it's all of them, except that the particles have been rearranged in the time since the Big Bang. So out of the Big Bang emerged all the matter in the universe, and that we know now includes dark matter particles, whatever they are, as well as all the normal particles. So within seconds after the Big Bang, all the quarks existed and had formed into heavier particles, and then electrons and neutrinos and the other light particles existed. And those particles have been part of the universe ever since. And the only thing that's happened with them since is that they occasionally have been built upon and rearranged in the fusion inside stars. So most of the universe is hydrogen plus a little helium, also produced in the Big Bang, and then subsequent to that, stars have converted much more of the hydrogen into helium, and some of the hydrogen and helium into heavier elements, but a small fraction, it's less than 1%.
Thank you. The next question is from an email from Sandra Gibson, who asks, if a black hole slowly evaporates through Hawking radiation, would the information trapped in it eventually be released again?
That's an interesting research question, and we don't basically know the answer. There's the holographic theory of black holes, which supposes that information as it falls onto the black hole is not completely lost. It disappears into the black hole, and beyond the event horizon we can't say what that information is or was. The holographic theory has the fact that the information may be coded on the surface of the black hole as it falls in, like a hologram. And then what happens when the black hole evaporates? A good question, and researchers simply don't agree. Some argue that that information can be tapped and released again, and others argue that the information is lost. Black holes may well have a firewall that sort of just deliberately or completely destroys information, and so there's no recourse where that information could ever come out again, even if the black hole evaporates.
The next question is from Oculus, who's on with us live. Do you think that time started the Big Bang, or that the Big Bang started time?
It's likely that the Big Bang started time, that time did not have a meaning at the instant of the Big Bang in this sort of quantum creation of the universe. Time was not a measurable quantity even. So time is an emergent property of the universe after the Big Bang, and it doesn't really have any meaning at the instant of the Big Bang, and then before the Big Bang, where even the word before is not very helpful, we simply don't have any theory of how to describe time.
The next question is from Abhishek, who sent an email. If it is correct that things do not touch each other, it's the force of repulsion we feel when going to touch something, my question is, why then do magnets attract each other if an electron revolves around an atom in the outer orbit? What's the concept behind that?
So magnetic force, magnetic attraction and repulsion is a different force. I mean, the electromagnetic radiation couples electric and magnetic fields, but we can also talk about electric and magnetic fields completely distinct. And magnetic fields that are distinct exert their own forces, and electrical fields that are distinct, that are just electrical fields, exert their own forces. The resistance that you feel when you touch something and your hand cannot pass through it, even though atoms are almost all empty space, is because of the electrical force and the outer electron shells of the atoms resisting And so that's a purely electrical resistance and no magnetic forces involved.
The next question is from Anthony Moore, who's on with us live. Can you please explain the ultraviolet catastrophe?
So the ultraviolet catastrophe was a phenomenon that in physics around the time of the early 20th century that almost precipitated the quantum revolution, the birth of quantum mechanics. If you calculate in a cavity, if you have radiation in a cavity in a sort of container, and you calculate all the modes of that radiation, and you do the simple classical calculation before quantum mechanics, so just using electromagnetic theory of Maxwell and the physics of Isaac Newton, basically, you calculate that the number of modes of radiation in a cavity at a certain temperature increases exponentially towards short wavelengths. So there are more and more modes of radiation at shorter wavelengths, and it just ascends rapidly. And that is a catastrophe because it's divergent. If you then integrate the energy of all those modes, you calculate infinite energy. So something in the calculation is going wrong. Something is failing. There cannot be a rapidly increasing number of modes to shorter wavelengths, the ultraviolet modes, or the catastrophe. And that's why it is a catastrophe. And the solution to the catastrophe is to think about radiation in a completely different way. A calculation only blows up and leads to a catastrophe because you view radiation as a continuous phenomenon. If you employ the quantum theory of Max Planck, then the quantized radiation circumvents the ultraviolet catastrophe. And so the quantum revolution, was not designed exclusively to solve this problem, but that issue in classical physics was a trigger to the quantum theory development early in the 20th century.
The next question is from Mr. P, who asks, do white holes form in relationships with black holes, or are they separate objects?
White holes are hypothetical objects, so they could exist in general relativity, but we have never observed one. We don't know a mechanism where they would be generally produced. And so it's not a tested proposition of physics. So I think just talking about them is simply speculation. They might form in twin with black holes, but as I say, we've never observed them, so they may not exist in nature. Oh, you muted.
Sorry about that. The next question is from Faisal, who asks, to what extent is it possible to send astronauts to comets and asteroids near Earth to retrieve samples?
It's certainly possible to send astronauts to retrieve samples, but the truth is it's much easier and better to do it robotically. The inner edge of the asteroid belt is really very far. It's obviously beyond the orbit of Mars, and Mars is a year-long journey for astronauts. So getting to the asteroid belt is a several year, 3 to 5 year journey, and then back. So we're talking about a decade. And the spacecraft that would be required to keep one or more astronauts alive and safe for a decade is an enormous thing. So it's simply prohibitively expensive to send people out as far as asteroid belt, even near Earth asteroids. And so robotic probes are always going to be able to do this, testing samples, perhaps even redirecting the asteroid, as NASA demonstrated with the DART mission, to come closer to the Earth and explore it in more detail, is going to be done with robotic spacecraft probably for the next decades.
The next question is from Andrew Wang, who asks, how is it possible that light is both a particle and a wave?
Well, the duality of light as a particle and a wave is sort of built into modern physics and quantum theory, because depending on the experimental situation, light has different properties. Light clearly carries energy and momentum, and so it acts like a small bullet, and that means it's like a particle, and that's demonstrated with the photoelectric effect, for example, in sort of foundational physics. And light has long been known to have wave-like properties, and that's been known, since the time of Thomas Young over 200 years ago, where light suffers interference and diffraction and refraction. And these are purely wave properties, not easily explained by particles. So we have a set of observations that are light as a particle or particle-like, and light that is wave-like in its properties. And both realities must coexist. And so the wave-particle duality is an established part of physics now for 100 years.
The next question is from Jeff, who sent an email. We see mutation all throughout nature. And we live in and have explored such a tiny portion of the universe. How do we know that we are not in a portion of the universe that is somehow mutated or, different than the rest of the universe?
It's a presumption of physics and science too in general that our situation is not anomalous, that we do not have a privileged or special situation in the universe. So everything we've seen in the history of astronomy tells us there's nothing unique or special about our universe or our place in it, either the star we orbit or the galaxy we inhabit or the region of space-time in this big expanding ancient universe. It is possible that there's something anomalous or weird about our sector of space-time, but nobody's been able to identify that so far. So it's a much better assumption, is the principle of mediocrity, that we are not special in any of our physical properties in this part of the universe.
Kelly is on with us live and asks, do the magnetic fields of Io and Ganymede that are connected to Jupiter's magnetic field somehow help Jupiter to have a stronger magnetic field itself?
Not really, because they are very small moons compared to the size of Jupiter. So the strength of their magnetic fields is tiny compared to Jupiter's. So we see the effects of those moons' magnetic fields because there's Io especially has a plasma torus, and that means there's high energy particles. Radiation has caused normal gas to turn into a plasma where the electrons are removed. And then we see the effect of the magnetic field on those charged particles. So we do have good evidence of those magnetic fields of the moons, but they are dwarfed by Jupiter's magnetic field.
The next question is from Jose, who is on with us live. Can we be sure that dark matter is really a type of matter?
Not directly. We imply that dark matter is a type of matter because we've been able to rule out other things that could give the gravity that we see on large scales that holds the Milky Way and other galaxies together. We've ruled out, for example, black holes. We've ruled out substellar objects. And we've worked our way all the way down to subatomic particles. So whatever dark matter is, it has to exert gravity because that's how we detect it. That's how we infer there's a missing component of the universe. And other things do have gravity. Radiation, has an equivalent mass by E = mc squared, so it exerts a very small amount of gravity, but not nearly enough to explain dark matter. So really, the amount of dark matter, the fact that it's 6 times more than all the normal particles in the universe, really says it almost has to be some form of matter, probably a new fundamental subatomic particle.
The next question is from an email. Ksenia asks, is life on a planet with a double star any different from life on a planet with one star?
It probably is, and it depends on the nature of the orbit. If the double star is in a very tight orbit and the planet is well beyond that, then it won't be much of a difference because the two stars will be seen close together in the sky. The radiation will add together. The difference, however, if the stars are in tight orbit, is probably that they will be very active. The stars will be active. They'll have more solar storms. They'll have more flares. They'll be more disturbed by their interaction. And that is probably damaging to life on a planet around a double star. On the other hand, if the double star is a wide separated binary, it is possible for planets to orbit both of the stars of the binary system without interacting with each other or being ejected by the interaction of the two stars. And then you would have also a situation where the planet sees one very bright star in its sky and then a much fainter binary companion star elsewhere. And that would not probably have a dramatic effect on life.
The next question is from Harry, who's on with us live. When two black holes collide generating gravitational waves, is there a directional plane or are waves generated in 3 dimensions?
That's a good question. It does depend on the geometry of the collision. So when black holes collide, they have a spin axis because black holes are almost all rotating since they formed from collapsed stars that were rotating. And as they inspiral towards each other, their orbital planes or their angular momentum vectors do sometimes align. So there is a preferential equatorial or rotation plane for black holes as they merge. And that indeed does create a non-axisymmetric signature for the gravitational waves or radiation. So it does emerge, the radiation does emerge in all three dimensions because the space-time is perturbed in three dimensions. But it's not completely isotropic. It could be stronger and typically is stronger in the equatorial plane of the merger.
The next question is from an email. Ion Khan asks, we know that our universe is expanding continuously. Is it an ideal condition, as that is to say, does the expansion of the universe somehow experience any type of friction or resistance?
No, because the expansion of the universe is a phenomenon of space-time itself. Space-time is the medium, if you like, of the universe. It's not what's in the universe. It's the construct itself. It's the metric of the universe. And so there's no resistance of the metric. Whatever is causing space-time to expand is not experiencing resistance. It is, however, retarded by the mass in the universe. So the presence, even though dark energy is making an accelerating expansion, there's a countervailing force from the dark matter in the universe which is acting, in a sense, like a viscosity or like a slowing down of that cosmic expansion. But at the moment, dark energy is twice as strong as dark matter, and so the universe is expanding faster and faster.
The next question is from Etham, who asks, can dark energy transform into dark matter, or for that matter, back and forth the other direction? Is there a connection?
It does not seem that there's a connection. It's natural to wonder when we have two major components of the universe that we don't understand, and they even have names that are similar, that they might be related. But at the moment, it does not appear that they are related. Dark matter appears to be a gravitational effect caused by a subatomic particle that we haven't yet identified. Dark energy seems to be an effect of space-time and a force that we don't really understand in physics. And so these are quite different things. One is a sort of matter or originating entity, dark matter, and the other is a sort of space-time energy originating entity, and we don't see any reason to relate them.
Barbara Getman sent an email asking, when a star is dying, gravity exceeds the pressure and the star collapses. So how are the outer layers of the star ejected? Why is the nebula not pulled back into the star?
So what happens is interesting. When in the final stage of, especially of a massive star's life, when the last fusion reaction ends, and typically it ends with iron because it's the most stable element, so no energy is gained by fusing beyond iron. As fusion ends, the pressure support of the star is lost. The inner region collapses essentially towards the end at a speed of light extremely rapidly. But in the middle, when it gets to the center and collapses and compresses, an object like a neutron star or a black hole has nowhere to go, and so it bounces. And so in the bounce phase, the gas that had been falling in and then squashes a new compact object heads back out, again almost at the speed of light, and forms a blast wave, a relativistic blast wave. And it's that blast wave that fuses many of the heavy elements all the way up to the uranium-type elements. And that's why you have an expanding nebula that goes outwards, and it's why all the material doesn't all end up in the center of the object.
The next question is from Anthony, who's on with us live. Can the planet Jupiter ever become a star?
No, Jupiter is a factor of many short of being a star. In the science fiction of Stanley Kubrick, or sorry, not Stanley Kubrick, Arthur C. Clarke, there's the hypothetical if you've added enough mass to Jupiter, you could trigger it into becoming a star. But you'd have to grow Jupiter's mass by an order of magnitude for it to be a star, so it's not even close to being a star.
The next question is from Suhail, who asks, Professor, what does the constant big G represent or signify? What does this constant, 6.67 times 10 to the 11 mean in our real life?
So the gravitational constant, denoted with the capital G, is a fundamental constant of nature. It first emerges in Newton's theory of gravity, and the fundamental force equation of Newton's theory is that the force between any two objects is inversely proportional to the square of the distance between them and proportional to each of their masses. And the constant of proportionality is the gravitational constant. The measurement of that gravitational constant is a fundamental property of gravity and the universe, was first done in experiments in the 17th and 18th century. The Cavendish experiment, Henry Cavendish did a famous experiment on this, and over time it was measured with increasing accuracy. So it is a fundamental physical constant associated with the strength of the force of gravity.
The next question is from Hasnain, who's on with us live, or Ahmed Hasnain, who asks, Hasnain Ahmad, asks, what is the definition of life that scientists use when looking for it in the universe?
Scientists don't agree on a single definition of life. You can find definitions of life on NASA's website. Biologists have given varied definitions of life. And there's a set of attributes that it has. I mean, the typical definition of life is something that is self-organizing, is reproducing, is evolving and changing its properties, utilizes energy, stores information in a biological sense, and is subject to natural selection. Now, that's a long list, and we don't know if all of those requirements are necessary for life. It also doesn't talk about ingredients. Is water required for life? Does life have to use carbon chemistry or need it not? So once you open up the can of worms of defining life, even biologists will argue for a long time about it, because while we only have one example to study, we can't talk about the general case, which is a tension, if you like, when you're trying to look for life elsewhere that might be different from our life.
The next question is from Kelly, who is on with us live. If energy is quantized, can this also be true for space and time?
It's certainly possible that space-time is quantized. In general relativity, space-time is a continuum. It's a manifold, mathematical term for a continuous entity is a manifold, and so it is continuous. But in the idea of quantum gravity that we're working towards, the ultimate theory, it's indeed plausible that space-time is quantized, that space has a fundamental discrete nature, and that time has a discrete nature, because time is continuous as far as we can tell in the universe we inhabit. So yes, it's quite likely that space-time is quantized, but we do not have the physical theory to express that at the moment.
The next question is from Studio Tracks, who asks, are there sonic waves in space? Did the Big Bang create noise like an explosion creates on Earth?
There are sound waves in space. Sound can only travel in a medium, and the universe is extremely thin plasma for the most part, but it's not empty. It's not a pure vacuum. So sound is possible. And people have done sonification or creation of a sort of analog sound of the early universe, of the Big Bang itself in the first few 100,000 years, because the Big Bang was a hot gas. And it was also quite dense for a while. The nature of the sound produced will depend on the density of the gas and the speed of sound in that medium. And typically on cosmic scales, these sound waves are extremely low frequency. So for any sonification experiment where you want to listen to it, you have to artificially bump it up by many octaves to be able to be in the audible human range.
The next question is from an email from Wendy. Can you explain what spontaneous symmetry breaking is regarding the Higgs field, and why would the force carrier boson for the Higgs field be so unstable?
So spontaneous symmetry breaking is a principle in physics where an underlying symmetry that pertains at very high energies is broken at lower energies. That's the general statement. And so we can see this in different cases. And the Higgs field at high energy, or in its natural state, has a high degree of symmetry, but that symmetry can be broken at lower energies, and then the Higgs field has to take a particular orientation, and the Higgs boson has particular properties. So spontaneous symmetry breaking at low energy situations gives particles very particular properties that they wouldn't have had at higher energies.
The next question is from Ellensburg, Washington. The question is, how is it possible to see large structures in the universe like galaxies form a ring? And let's see, what should we make of it when we see these kinds of ring structures or things that seem sort of ordered like rings?
So ring galaxies have been known actually for decades. So just in surveys of the nearby universe using photographic plates going back 50, 60, 70 years, we found galaxies that had ring structures, and the most common type were called polar ring galaxies, and they're almost always due to interactions or collisions, slow collisions between galaxies. Depending on the nature of the collision, the interaction can eject a stream of stars that eventually coalesce or form into a nearly ring shape. And so it is a natural phenomenon that we can see. And this will happen in the early universe too, because galaxies were growing then and interacting much more frequently in a denser universe. So we think ring galaxies at any redshift or in any distance from the Earth are caused by galaxy interactions. And simulations with supercomputers sort of show how you can get ring-like geometry. So it's it's not a common situation. You only ever expect a very small fraction of galaxies to show it, but we understand how it happens.
Rereading the question, I think I misunderstood a little bit of it too. And so I guess a follow-up is, how likely is it that we can see large structures in the universe, like galaxies, like many galaxies that form some ring type structure in the galaxy? So like how large of a structure can we observe in the universe?
Well, there are very large structures in the universe that are associated with what are called baryon acoustic oscillations, or BAOs, and that is a quite subtle interaction of the plasma that exists in the intergalactic medium between galaxies and the microwave background radiation from the early universe. Essentially, you can have resonant phenomena with that, where you have characteristic scale of these oscillations of this plasma, and those scales are very large, like 150 megaparsecs or 200 megaparsecs. That's 500 million light years, and that signature of a ring, essentially, that's what it looks like on the plane of the sky, has been seen in data. It was seen first about 10 years ago in Sloan Digital Sky Survey data, and it's been seen more recently than that. So that's the largest scale of structures that we've seen in the universe.
Excellent. Thank you very much. It's now 11 o'clock. We are going to take one final question for today, and then we will wrap up, and we'll talk about the next session. The final question for today is going to be from Kazi, who asks, "Sir, what are your thoughts on the existence of aliens?"
Well, aliens mean advanced creatures off Earth. I think it's almost certain that there are microbial organisms outside the Earth, because we know of billions of habitable worlds in the Milky Way, and they have all the ingredients that are needed for biology. And so I think it's very unlikely that there are not microbes elsewhere, because Earth formed microbes quite quickly, and for most of the 4 billion year history of life, most life on Earth, most species, most genetic real estate is taken up by microbes. Aliens, or advanced creatures beyond Earth, is much less certain, because, for example, it was in the 90% of the history of life on Earth over 4 billion years, you'd need a microscope to see the life. It's all microbial, and often just single-celled, not even multi-celled. So it took a long time on the Earth, and then creatures like us and plants and animals have only come around in the last few 100 million years. So maybe it's rare, maybe it takes a long time, maybe it's hard, maybe it doesn't happen very much. But I guess in the totality of the statistics of habitable worlds, it would have to be incredibly unlikely for advanced life forms not to evolve, for it not to have happened anywhere else than the Earth. So thanks for that question, and the range of questions today was very good as usual. And I think we have one more on the books for early March. Then I have some travel coming up, so we may space out a little more after that. Thanks to Matthew for running the session, and we'll be back with you in a few weeks.
Excellent. Actually, our next session is Monday, March 18th. So we have a 3-week break, and then we will be back here on this channel. So if you have not subscribed, make sure you go subscribe to this channel and click that bell icon. If you scroll all the way back to the top of the chat for this live session, you can see there is a group that you can, like a Google group that you can join. And I will send you emails announcing upcoming live sessions if you're not on our class mailing list. Other than that, we will look forward to seeing you in a few weeks. Take care, everyone.